Hi guys, we are continuing with solving our Leetcode problems, and today is the next task for binary search. So let's check. And today's task is about Koko eating bananas. So let's check. So we have some Koko that loves eat bananas, and there are n piles of bananas. Okay. Uh, the eats pile has pile I bananas. And the guards have gone and will come back in 8 hours. So Koko can decide her bananas per hour eating speed of k. Each hour, she chooses some pile of bananas and eats k bananas from the pile. If the pile has less than k bananas, she eats all of them instead and will not eat any more bananas during this hour. Okay, so Coco likes to eat slowly, but still wants to finish eating all the bananas before the guards return. So we have to return the minimum integer k such that she can eat all bananas within 8 hours. So for example, here we see like 3, 6, 7, and 11. Yeah, and we have h8. Okay, so we have n piles of bananas. So okay, so we have n piles. We have some n piles of bananas. Okay, and each pile has some number of bananas. So for example, here we have 3 bananas. On second pile we have 6 bananas. Then we have 7, 11, and so on. And we have some age guard that has gone like for 8 hours. And Coco can decide her bananas per hour eating speed of k. Okay, so for example, we can tell, okay, my eating k is 11 bananas per hour. And yeah, so for 4 hours, it actually can eat all bananas. So is it correct intention or not? So each hour, she chooses some pile of bananas and eats k bananas from the pile. If the pile has less than k bananas, for example, 3 is less than 11, and she eats all of them instead and will not eat any more bananas during these hours. Okay. Coco likes to eat slowly, but still wants to finish eating all the bananas before the guard return. And we should return the minimum integer k. Oh, okay, so we should return like the minimum speed such that she can eat all the bananas within 8 hours. Within return the minimum integer k. So we should return the minimum speed. So the numbers of bananas per hour such that she can eat all the bananas within 8 hours. Okay. Within 8 hours. So that she can eat all the bananas within. So okay, so we should like stick to this 8 actually. So for example, if we like take 11, then we can eat like all bananas with 4 hours, and we need to eat it for 8 hours. If we choose, for example, 6 as our value, then we can eat 2 bananas per 2 days here, and here also 2 days. So in total we have 6. Okay, then if we choose 4, for example, so we can eat this banana as 1 day, then 2 days, 2 days, and 3 days, right? So in total, we have 8 hours, and the speed would be 4. What about here? So here we have like 5, so we should eat all bananas for 5 hours. So actually, I think, so first intention is when we have array of element. Okay, so I think that I quite understand the problem. So we have piles of bananas. So let's say like 10, 4, 6, 1, and we have some age. So it's number of hours when our guard has gone. Okay, and in this case, like for example, 4 or 4. So to have to eat it in 4 hours, we need to eat all bananas per each day. So to eat this banana per 1 day, we should return would be 10 in this case. Okay, let's think about some constraints. So the first constraint actually about piles. So I expect that on the pile we will have at least one banana. We actually can have empty pile, but I expect to have at least one, and also we can have like 10 in the fifth power, let's say, bananas. The second constraint is about piles lengths. I also expect to have at least one pile here, and let's say also 10 in the fifth power. So it's not sorted. It can have duplicates, I believe. And age, it's actually also how many hours our guard has gone. So I expect he go at least for 1 hour, and here like 10 in 4 power. Let's check constraints. Okay, so pile lengths almost the same. Age, okay, so from 1 to 10 in 9th power. Okay, so we have guard that can went for 1 billion hours. Interesting. And here as well we have piles that would equal to 9 power. Okay, good. Let's think about solutions. So first solution. So we have age. If our age is equal to the size of array, then we should actually take the maximum. Age should be equal or greater than pile's length. So actually we can't have situation when we need to eat 2 piles per 1 hour. So that's intention. Yeah, so that's quite important to mention here. So it would be piles lengths. Okay. So we can have equal or or more 1. So if we have, for example, such situation, let's consider before solutions, let's consider some examples. So here's the first example. Yeah. So we have 5 piles and we have 6 hours. It means that 1 pile we should eat for 2 hours, and all other piles we should eat for 1 hour. So actually how it can be solved, we can find the next greatest pile. So the next greatest pile would be 23. And yes, and to have h mod piles lengths, and here we have 1, and our results would be actually piles length -1 and minus I, where I is our mod, this one. Okay. Let's check this intention with other test cases. So for example, we have the same, and we have 7. So 7, it means like 2 piles we should eat for 2 hours, but 1 pile we should eat for and 3 piles we should eat for 1 hour. So actually it's, it's our 20 here. Yeah, because if we have 20, then we have 2 piles that would be eaten for, yeah, so 20 here, it also works. As well, like 8. 8 here, it would be this one, 9. 9, it would be this one. But 10 is interesting. 10 is, means that all our piles we should eat for 2 times, or at least, like for example, we can eat 1 pile for 1, then second pile for 2. It's interesting. Okay, so if we sort again all our piles, and we should eat them for 10 hours, what should be our speed? So we can try, I think, with 4. So 4 we eat for 1 hour. This one we will eat for 3 hours, right? This one with 4 we will eat for, for 5 hours. Yeah, so we have like 20, we have 20, 24, 28, and 32, actually, yes. So we have 8, right? For 8 hours. So in total, it would be much more than 10. So it means that we should consider some bigger number than 4. So yeah, if we will take 4, we will have such speed actually. Okay, so let's check. So we have, and what is it possible to have such case when it's not possible to have to eat within this number of hours? Okay, for them, yeah, maybe I can try with maybe I can try with 6, for example, then. Yeah, if it would be 6, then I have here 2. Here I have 4. Yes, here I have 4. Yeah, because if we will divide 20 by 6, it would be 3 and something. So yeah, so it would be mod plus 1. Here, yeah, so here it actually, yeah, here we have what? We have 4, right? Because 24, it would be for 4, and 18, it would be for 3. So we ate it as well for 4 hours. And then we have 30. And yeah, so if we divide 30, it would be 5 hours for us. Exactly 5 hours. So in total, we can see that when we take 6, it's actually 20 hours. So we should take some more like other value, not 6. It's something in between 4 and 11, because for example, if we will take 11, we will eat this one for this, yeah, then this one for 2, this one for 3, and this one for 3 as well. So in total, it would be 5, 10. Yeah, so if we take 11, it would be exactly 10 hours for us. Okay. Interesting. Yeah, it's interesting. But if we have like 30, then we have 5, right? 5 hours. When we have 23, we eat this for 4 plus this 2, 6 hours. Then we have 20. We eat this for 3 and another one for 2. Yeah, so we have 5, 3, 3 plus. Then we have this one, and this one would be 10, and then we have this one, so we eat 4 for 1, and all other would be greater. Yeah, if we'll take something in between. Okay, so what can we do? Okay, so what we can we do actually, I think. So the lowest number of hours that we can take, I think it's 1, right? In our case, it's 1. If we take 1, it would be our lowest value. And we should check, for example, we sort this element, then we take the middle element, we calculate how many piles our Koko will eat during these hours. So if we take 12, 20, it means all elements on the left it will eat for 1 hour, so we don't need to calculate this, but we need to calculate for all of these values. That would be greater, because we don't know how much it would eat here. Yes. So we calculate, we check. So on this level, we can check. So if we have 20 and we have some age or number, we see that these piles would be eaten for 3 hours. Then we check, okay, here this would eat with 2 hours, this would eat with 2 hours, right? So as a result, we will have 7. So we check 7 with age, and we see that, okay, so it's lower, so we need to jump on another values, and then we jump to 11, and we check, okay, so with 11 it will eat this one for 1, then this one for 2, this one for 3, this one for 3, and then we check all these values once again, and And here we have 10, and this would be our result. If we don't have, like, if we have, for example, not 10 but 12, let's say, then we are going to jump. So now we are at 11 and 4. So we are going to jump on 4. So we calculate with 4. So for 4 it will take 1. For 11 it will take 3. For 20 it will take 5. For 23 it would take 6. For 30, yeah, it would take 8, right? Yes, and as a result, this would be 23, right? Yes, 23, and which we see that 23 is greater than 12. If it's greater than 12, so we found actually number 4, and we found number 11, right? So something in between 4 and 11 should work for us. And now we can actually jump something in between and actually check what would be our numbers here. So maybe, yeah, so maybe we should do something like this. So first we start yeah, we start at the beginning, and we start at the beginning and we try to calculate how many numbers, yeah, what would the speed work for us. And I think we can do it with binary search, but here it will be like 2 binary searches here, as I see. So first binary search, like to find 2 elements in between where we should find, and then again jump with binary search and calculate all these elements. Let's first try to find it without binary search, like to go one by one. So we check, like, we first sort array, start from the beginning, and try to find element that would be greater than that would be greater than our age. So here we found 4, right? So 4, we see that it's greater, yes. If it's greater, then we stop on 4. No, we should find where it would be less, okay. Yeah, so we start with 4, then we go to 11. Then we go to 11. And we found, yeah, it's if at 12, for 11 we calculate 10, so 10 is less, right? So we found this 10 that is less, so we are trying to find where it less. So first one would be always so first one here is greater, and next one is less, right? Yeah, okay. Yeah, okay, I think that I understand. So the logic is the following. So we are trying to find an element that would be element that is less than our age. If it's less, then we take the previous element actually, and this would be our boundaries to where we should go from the previous to our right boundary. And we found these boundaries, and then we are trying to go one by one and check when we will reach this age. So solution will look like this. So first find right boundary. Then the second one, before this we can like check edge cases. For example, when files length is equal to age, we should return the last element from sorted piles. Then I propose like to do 1.1 sort piles, 1.2 find right boundary, 2 find speed. Find boundary can be done with linear time, and find speed also can be done with linear time. But it would be not only linear time, because we should like go multiple times. So here it would be something like this. So we find right boundary for n squared plus find speed with also n squared. So the total solution here, complexity would be time with n squared, and space would be constant in this case. Okay, let's try to implement the solution with n squared and check if it works. So, according to our constraints, we have at least one pile. And what can we do? We can do arrays sort piles if piles length equal age. Then we just return piles h minus 1. Okay. Otherwise, we should find our right boundary, and we are going through each element. Where we take each piles, it would be current pile. And what should we do? It would be our current pile. So for example, in this example, if we take it, so what we done, we sorted first 4, 11, 20, 23, 30. Yes, so we sorted. Then we take 4 as our pile, and then we try to calculate like what would be our current speed. Current speed 0. Let's say current speed 0. And what we are going to do, we are going to start from j equal to 0, and j is less than piles length. So we are going once again, and we are implementing our current speed plus piles j. We divide by current speed plus piles j mod current speed. If it's greater than 0, we add 1, otherwise we add 0. Okay, so it would be current speed. And here, and this logic we can do actually with binary search. But for simplicity, let's try first linear approach. So we found our current speed. Then we should check if our current speed is greater than h. So for example, here we have h equal to 12, right? With 4, if we take 4, it's actually greater than 12. So, so here we should just continue going to the next element, actually. And for 11, so for 4, let's say, yeah, we calculated for 4, I think somewhere here. I think it's 23, right? Then we have 11. Yes, and for 11, we calculated for 11, I think. Yeah, so if for 11, it's 10. Yes, so we found that this one is less. So if it's less, yeah, first of all, if current speed. So if we found that it's equal to h, then we just return current pile. Yeah, we should divide not by current speed, but by current pile. And this one by current pile. Yes, we should return current pile. So if our current speed is equal to h, we return current pile. If current speed is less than h, we should have our right boundary. Our right boundary, its beginning is 0. If our current speed is less, so for example, for 4, we calculate that it's less, then our right boundary would be equal to our piles I. So we found our right boundary. Also, we can find our left boundary as well here. So we found our left boundary, and our left boundary would be equal to, if our I equal to, is greater than 0, then piles I minus 1. Otherwise, it would be 0. So we have our left and right here. Now we should do another binary search, or we can do actually the same approach here. So the same approach would be following. We start our iteration while right minus left is greater than 0. Okay. And somewhere in between of right and left, somewhere in between. So we are trying to move our left pointer and to calculate this number like the current speed. So somewhere in between, we should find this solution actually. So let's try, to return -1, because here I suppose that we will never occur. So let's try to calculate. So we start with left, and left is our current pile, right? And our current speed would be 0. We do the same approach here. So we are going from left to right. It's current piles. Okay. Yes, so we are going from left to right. And yeah, what should we do? Yeah, we should do the following. We should take these piles values. So we start from, we iterate like from piles for each pile. And current pile, it would be our left. So we divide by current pile, we increment our speed. We take this current pile, mod, so we calculate this speed actually. And if our current speed is equal to h, then we return current pile. Otherwise, we increment our left by 1. Yes? I think we run out of time here, but let's try to, we have some test cases here. So let's try to dry run, for example, this first test case. Okay. So first, what we are doing, we are sorting this array. So it's already sorted. So we don't actually do anything here. We check. Okay, so h is not equal to h. 8 not equal to h. So we just, we just do this calculations here. Left would be 0, right would be 0 at the beginning. What we are doing? So current pile, we are taking current pile, that would be 3, and current speed would be 0. Then we try to iterate. Okay, so we take current pile 0, 3, divided by 3, it will be 1, and we have 3 divided by 3 mod, and it would be 0 actually. So current speed, let's try like 3, like 1 for 3. Then we have 2. Then we have 7 divide by 3, it would be 2. But we have mod, so it will be 3 for us. Then we have 11. 11 divided by 3, it would be 3, right? But we have another one, so we have 4. So if we will count it, it will be 10, right? Our current speed will be 10. And we are checking that, okay, it's not equal to 8 that we are looking for. It's greater. And 8 is also not greater than current speed. So we go to the next pile. And next pile here is 6. So current speed again 0, and we calculate for 6. 6 divided by 3 would be 2. Here it would be 2. And it's not correct. It's not correct. So I think we should do something like this. If current pile is greater than piles j, then we should return 1. Otherwise, we should do these calculations, actually. Yeah, if it's less. Yes. Or let's say even greater or equal. Now I think it should work. So here it would be 1, then it would be 1, then 6 is less than 7. So we divide, it would be 2 here. Then we have 11. So 11 we divide by 6. It would be 1 plus 1, 2. So in result, we have 5 and 6. 6 is current speed. So current speed, and it's not equal to 8, but it's less. So our left here, it's equal to, so currently I is 1. So our left is going to become piles I minus j. So we are taking 3, and right, it would be 6. So here it will be 3 and 6. So something between 3 and 6 will give us 8. So let's make it 3. Write 6, okay? So let's check. Okay, so our current pile would be 3. Current speed 0. We are going again by this logic. So by this logic, and we are taking our array of piles. Okay, so we calculate for 3. For 3 we have 1, then we have 2, then we have 3, then we have 4. So we calculate, we see that actually it's greater than 8. So to the next one. Left, we increase our left. So our left would be not 3, but now it would be 4. Okay, I need to check to take charger, so wait a minute. Okay, let's continue. I will try to charge it. Okay. Okay, let's continue. So we have 4, and when we have 4, if we calculate it, then we have 1 speed, 2, 2, and 3. And we see that it's equal and we should return. So let's try to run it. Incompatible type in can be converted to Boolean. Okay, I think that I didn't copy all the code. So let's try to copy this as well. Okay. And put it here. Let's run it. Okay, interesting. So we have wrong answer here. Why? We have -1. Okay. J. Yeah, somewhere we have bug here. I think we have somewhere bug here. Let's try to print left and right. Let's run it. Left, we have 7 and 11. So yeah, this is not correct actually. So we probably hear problem somewhere here. Let's try to print also how our sorted array looks like. Yeah, for sure we didn't solve it in the time, but I like to check why it's not working. Okay, so let's also try to print all our speed, our current speed for I, and let's try to print it. Run. Okay, so yeah, to print it correct, we should use arrays to string, because we print in not values, but we are printing a reference. Arrays to string, no suitable method for sort. Okay. Yeah, so let's print it afterwards, but here we just sort it. Yes, we should put it here. Run. Okay. Yeah, so we see that it's sorted correctly. Then we have 10. Our current speed would be 10. 10 for I equal to 0. So when we have 3, right? So when we have current pile and we have like current pile is 3, and we check, okay, so our current pile is greater or equals than 1, we should return 1. Okay, so here it would be 1. Then we have 6. So current pile is not greater than 6. So what we are doing here is actually we doing this division. So we 6 divide by 2, and then we take mod. Okay, so we have just 2. Then we have 7. We do the 7. We have 3. Then we have 11. We divide by 3. Divided 4. So indeed, we see that for I equal like to 3. Let's say for current pile, for 3 we have 11. But what is interesting is that for 6 we have only 1. Why? This one is interesting for me. Yeah, so for 6 I have 6. Why? Let's check. So our current speed is not less, so it's 10. So h is not greater than current speed. So we go back here, we increment our I, it will be 1. So we take next pile, it would be 6. Our current speed would be 0. So then we calculate, we take from 0 piles, 0 would be 3. Current pile is greater than piles, so we take 1. Then we again take 1. Then we have 7. So 7 is greater than current pile. So what we are doing, we take this 7, divide by 6, would be 1, plus 1, it would be 2, right? Then we take 11, right? And 11 is greater, so we 11 divide by 6, it would be 2. 11 divided by 6, it will be 1 plus 1, it will be 2. So our calculation is correct. So here is correct, it's actually 6. For 6 we have 6. Then here we should break, actually we should go out from our array. So let's check. Yeah, so now it's accepted. So let's submit it. Okay, so we have another use case. We have arithmetic exception divide by 0. All right. Line 68. Okay. So here we have current pile. Okay. So I have 1. And then, yes, and then let's use this test case. So we have this element and this element. And run. So I think for this, maybe it will be time limited exceeded. Yes. So time limit is exceeded. It means that we should try to implement binary search here and not doing this for loop. Okay. So let's first, yeah. So I think that this one is actually depends on the length of array, and we have only one array. So for current test case, we should optimize this portion of code, actually. So to optimize this portion of code, we should do binary search. So how our binary search would look like? So it would look like the following. We have our left and right, correct? Left and right. And we should jump into the middle of our elements and try from the middle to calculate this current speed. So current speed is useful for us because with binary search we should with binary search we should find current pile actually. So so let's do the following. So if right minus left is greater than 1, we should do binary search. How we are doing actually binary search? So we find the mid pile. Mid pile is actually found like this: right minus left divided by 2. Plus do not have overflow plus left. So it would be our mid pile that we want to take, for example, right? So when we calculate for 5, when I calculate for 5, it means that current speed is less than what we want to find. So we need to move our right pointer. So our right should be equal to current pile. Here, our left to current pile. And here it could be that should be like +1 and -1. Let's check. Would work. Okay, so it's faster, but we see that it's not actually working. We have output -1. What would be if we will do something like this, just something stupid? Yeah, we still have -1. Okay. Okay, we still have -1. Yeah, because I think that we are moving our left pointer all the time. Let's try to debug this code and to find out the solution. So we have left and right. Let's comment this one for now. So we have left that is equal to 1 and right that is equal to this one. So let's try to do print here system out println, and here we are printing our current speed plus current pile. So we are receiving current speed for current pile. And h here, what is h here? Let's also print h. Like h equal to h. To h. Okay, and let's run it. Okay, so yeah, this h, let's go here. Let's run once more. Yeah, so we have h something like this. So what we are doing, we calculate, like we see that current speed for current pile. So if we will take this pile, this pile, and we should find this h, so it's less. So like two times we should check like to get this on. Let's try to find, maybe we should just check to our long. Maybe it's problem with long. No, I think it's not problem with long. So we just have millions. So it's, yeah. So it's not problem with long data structure here, right? And we have all in ints. So, okay. So it's not problem with long data structure, but we have two. So two is definitely less than what we want, right? And this means that we should move two is less that we want. So we should move our right pointer, our left pointer. So it's where our current speed. Let me think. So is 2 when we have less, then we should write to less element. Yes, right to less element. So then let's take it out and let's do it here. Okay, so we have first this one, then we see that we have two. Why we here have two? Because we are not moving our left. Like we calculate our current speed, current file. So we just move, okay. This one is not correct. Yes, but still. So we move our right pointer. We calculate 4 times, then we again move right pointer. For this value, we calculate that it will take 8 times. Then we again move our right pointer 16 times. Move. Yeah. So we are moving our right pointer until we will get the number of times that we need. And our speed is actually this one. And expected is 2. So we check like 1 and 3. Okay. Yeah, so we move our, okay. So here it should be right, I think. Something like this. Yes, and let's submit it. Okay. Here we have another wrong test case. So let's take a look. We output yes. Okay, so here we have left and right. So in some cases it can be left, or in some cases it can be right. So I believe that in the end we should calculate the speed one more time for left and right, and then decide. Then we should decide whether we are taking left or we are taking right. So current speed, so we should calculate current speed one more time. First for left, current pile. So current pile first left. Let's make it like current speed 0. So left, first left, and we are checking if left is equal to h, we return left, otherwise we return right. Yeah, it's all like this. If current speed is equal to h, we return left, otherwise we return right. Let's run it. Okay, let's take this wrong example. NH, run it. Okay, it's run. Output 2. Expected 1. Okay. 1, 3. We have 1, 2. Expected 1. And this would be our H. So let's try to print it. Okay, so our current speed would be equal to left. And it would be final result. Let's run it. And let's check. Okay. So for 1, we have final result something like this. Current speed left. And to get it H. To get it H. Okay. Okay. Yeah, so I think that we calculate like current speed, and we see that actually like speed would be here, but we should wait for this number of times. And yeah, so here we can check. Yeah, so here what we can check, that if h is greater than current speed, then we should return 1. Okay, so we have another test case. I have another test case. Here it will be right. Let's do it like this. Yeah, let's also use this test case. Then run it. Okay. So yeah, let's have it here. Run it. So we have output like this, but we expect like this. So at the end, we have just two values for 9, 20, 18. It will be our right. It's interesting, like what would be our current speed? I'm interested also in left and right. So final, left and right. Let's run it. Do we have correct result? Okay, but so we are ended up somewhere here. Okay, so we have current speed, the current pile. H equal to 10. Output. Okay, so when we calculate for 9, okay. Then we have this one. Okay. But what would be here? So we see this thing, current pile. For 10. And we return current pile. Output. But it should be another one. Maybe here we have this problem with long. We have 1 billion. Maybe we have this problem with long. Here, maybe we have this problem. Let's try with long. No. Okay, 3. Yeah, I think it should be not any problem here. Okay, so we are receiving 10 current speed and h. Current speed 10. So we calculate current speed like 10 with this number of current pile. Okay. So for this pile, we calculate that current speed would be 10. But actually it's not the lowest current speed. So that's actually the problem, that it's not the lowest current speed. So it's so it's kind of speed that we can get 10 elements, but we can get it with lower number of speed. So it's not the lowest speed that we can get. So what I think here, that maybe we should not return from here, but calculate all the speeds and then go somewhere here and do this. Okay, submit it. Okay, we have another wrong answer. But yeah, but here I think it's easier one. Maybe not easier. Okay, let's check. Okay, so we have 2 piles and output expected 1, but we output with 2. Okay, let's check why. So we have 2, 2, and 4. Like to have 4, to have a speed 4 with piles 2, output should be 1. Because if we have 2 as an output, yeah, so I think here, yes, so here we should do this thing. We are calculating our current speed. If its h is greater than current speed, it's return true. But if current speed yes, h. So if current speed is equal to h, then we return left. Otherwise, we return true. Here. Let's run it. We return right. Let's submit it. Yeah. Okay, so I've solved this question, but yeah, for sure it's not the base time complexity here. And I think that it can be improved somewhere here by binary search, but let's check how it's done faster. Okay, so we can even done it more faster. So again, some binary search and can be done faster. Okay, so I think it's all for today. Thank you. So I'm stop sharing. and have a good day.